Hello everyone, this is Catalin from the Coding Cave and welcome to another episode of my data science series. In today's episode we are going to talk about linear algebra and more specifically we are going to talk about vectors. So let's get started. Now let's see what vectors are. So basically vectors, or at least in computer science, vectors are a list of values which of course have a geometrical representation. So this is an example of a two-dimensional vector. So a two-dimensional vector has only two values. The first value correlates to the x-axis and the second value correlates to the y-axis. So the arrow here points to this point called A, which has the coordinates of 2 and 3, where 2 is the value on the x-axis and 3 is the value on the y-axis. Vectors can be also multi-dimensional, not only two-dimensional. For example, this is a three-dimensional vector. It has three values. The first value in the list corresponds to the x-axis, the second value in the list corresponds to the y-axis, and the third value in the list corresponds to the z-axis. So this is the geometrical representation of a three-dimensional vector. Here I have an example of a vector in Python. The easiest way to represent vectors in Python is by using Python lists. Of course, Python has a third-party library called NumPy, which is a more efficient way to represent vectors and do linear algebra calculations, but it is a lot simpler to just use lists, although not as efficient as by us using NumPy. Now we can do several things with vectors. One of them is adding vectors. So let's define a function called vector addition, which will take two vectors. Let's see, v1 and v2, and let's do the addition. So return v1i plus v2y for v1i v2y in zip of v1 v2. So the vector addition is basically an element-wise addition of the two vectors. I have some images of the vector addition here. So this is the geometrical representation of the vector addition. So if we consider the first vector being a side of a triangle and the second vector being another side of that triangle, then the sum, or the vector obtained by adding the two vectors, is a third vector which starts from the origin of the first vector and ends in the point where the second vector ends. This is another way to think of this addition. It is called the parallelogram rule. So instead of having just one triangle, you imagine having two triangles which form a parallelogram, and the diagonal of that parallelogram is the vector you obtain by addition, the sum vector. This is another image which illustrates vector addition. So as you can see, this is the algebraic relation. So it is an element-wise addition. You add the first element of the first vector with the first element of the second vector, the second element of the first vector, with the second element of the second vector, and so on, and you obtain another vector. And this is the geometrical representation. So this is the triangle rule, and if you think of it with a parallelogram, you also have the parallelogram rule. if you look at the whole image here. And here are some examples. So the vector 3, 2 added with the vector 6, 4 gives you the vector 9, 6. So you add 3 with 6 and 2 with 4 and you get 9, 6. And these are some three-dimensional vectors. So vector 2, 5, 1 added with the vector 3, 1, minus 1 gives you the vector 5. So 2 plus 3 gives you 5. 6, 5 plus 1 gives you 6. And 0 because 1 plus minus 1 gives you 0. So let's test our function here. Let's define two vectors. Let's say v, let's make it equal to 1, 3, 6, and w, let's say, or let's make it equal with 8, 4, minus 1. And now let's test our function. So let's define a vector z, which would be equal with the sum of v and w. And let's print our new vector z. As you can see, the vector z has the following values: 9 because 8 plus 1 makes 9, 7 because 4 plus 3 makes 7, and 6 because 6 and minus 1 makes 5. Of course, because we have vector addition, we can also have vector subtraction. It works in a very similar way. So let's define our function, vector subtraction. And instead of being an element-wise addition, the vector subtraction is going to be an element-wise subtraction. So v1 minus v2y for v1i, v2y in zip of v1 and v2. And now let's look at some images. Here I have an image of the vector subtraction. As you can see, while in the vector addition, the resulting vector would point from the starting point of the first vector to the ending point of the second vector. Here, the subtraction vector or the resulting vector points from the ending point of the second vector to the ending point of the first vector. So basically here, if we consider the resulting vector as normal vector and the b vector as the second vector, so let's say that a minus b is our first vector and b is our, no, let's say that b is our first vector and a minus b is our second vector. Then if we just apply the triangle rule, then a would be the sum of our two vectors, which is right, because if we add a minus b with b, we obtain a, because minus b plus b makes 0. So as you can see, the relationship is correct, and basically this is the parallelogram, not the parallelogram rule, but the triangle rule seen just a little bit different. I hope what I have said makes sense. If not, let's just go back to the image with the parallelogram rule now, not the triangle rule. So while the sum vector or the result of the vector addition is the larger diagonal of the parallelogram, the vector or the resulting vector in subtraction will be the smaller diagonal of the parallelogram, which really makes sense because if we do we do a subtraction instead of addition, our resulting vector should be shorter, not longer. So you can think about vector subtraction as that also. So just do the parallelogram rule, and this, instead of drawing the larger diagonal, just draw the shorter diagonal. So this one. Now let's test our function. So let's define the vector y to be equal to the result of v1 minus v2, and let's print our y vector. We don't have v1, we have v and w. And now it should work. So the result is minus 7 minus 1, 7, because 1 minus 8 is minus 7. 3 minus 4 is minus 1, and 6 minus 1 is 7. So the result is correct. Now we will move on to the next operation, which is scalar multiplication. So the scalar multiplication is the multiplication between an integer, or not really an integer, a number, a real number, of a float value, or any kind of number, with each element of the vector. So let's define our function, scalar multiplication, which will take a scalar and a vector, and will return another vector, which we are going to obtain by multiplying each value of our original vector with the scalar. So for v in vector. Now, of course, scalar multiplication has a geometrical interpretation too. So let's just go here. Let's make the image larger. So this image illustrates the scalar multiplication. So here is our original vector a. By multiplying it with 2, we obtain a similar vector having the same direction, but being twice as large. So the magnitude of the vector is multiplied with the scalar. We could multiply our vector with another value, for example 0.5, and we will obtain a vector which will have the same direction, but it will be half as short. You can multiply the vector with any scalar, and you will obtain another vector which will have the magnitude, or the length, the original length of the vector times the value you multiplied it with. And if we multiply a vector with negative values, then the direction will change. So here we have multiplied the vector a with minus 1, and we have obtained the vector a, which points in the opposite direction, but of course has the same magnitude. Now let's test our previously defined function. So let's take vector y and let's multiply it with minus 2. So let's call our new vector h, and our new vector will be equal with the scalar multiplication of y with minus 2, and let's print our new vector h. Here is our new vector. So our new vector has the values 14, 2 and minus 14, because minus 2 times minus 7 equals 14, minus 1 times minus 2 equals 2, and 7 times minus 2 equals minus 14. Now we will move on to the next operation, which is called the dot product. So the dot product, which is a little bit more complicated, but you can still understand it. Don't worry, it is not that difficult, but it is a little bit more difficult than the other operations. v1 v2. The dot product is going to be the product between two vectors, and the result written in mathematical form will be the following. So the first element, or the first element of the first vector times the first element of the second vector plus the second element of the first vector times the second element of the second vector plus, and so on until you reach the end of the vector, which would be the last element of the first vector times the last element of the second vector. So let's write that in Python. So the result is going to be the sum of v1i times v2y for v1 v2 in zip of v1 and v2. Now here is an example of a dot product. So we have two three-dimensional vectors. The first one is the A vector and the second one is the B vector. So you multiply each value with its corresponding value in the second vector, and then you add everything up, and this is called the dot product of the two vectors. The dot product of the two vectors also has a geometrical interpretation. So if you take the projection of the second vector on the first vector, and then you multiply the magnitude of that with the magnitude of the first vector, you obtain the dot product. And here is an alternative formula for the dot product, which would be the magnitude of the first vector times the magnitude of the second vector times cosinus of or cosine of the angle between the vectors, because the length of the projection of B over A is basically the magnitude of B times the cosine of the angle. This is basic trigonometry, so this is the geometrical representation of the vector. And now let's test our function here. So let's define another vector called O, which will be equal to the dot product. Well, O will not be a vector, it will be a number, because the dot product returns you a scalar, a number, not a vector, as you can see here, because you have a sum, not a list. It was my mistake. I was just going to say what I meant is that I have said that O is a vector, but actually it isn't. It is actually a number, so my mistake just a few seconds ago. So enough of this, let's continue. And let's make it the dot product of two vectors, let's say H and V. And let's print the value of O. So let's see here, we have forgotten the variable, and now it works. So just correct this, because we are iterating with these values through these vectors, through these lists, not with the vectors through the vectors basically. So it was just a mistake. Just correct it and let's continue. So the value of the dot product is minus 64. And now let's move on to another function. So now that we have defined a dot product, we can define what is called the sum of the sum of the squared values of a vector, which mathematically would be written vi times v1 times v1 plus v2 times v2 and times vn plus vn times vn. So basically you take each the value of each value of the vector, you multiply it by itself, and then you add everything up. So using our dot product function, it is very easy to implement this function. You just return the dot product of v and v. So let's test it. Let's compute the sum squared, sum of squares. Let's compute the sum of squares of the vector y, and let's print it. So the sum of squares of vector y is 99. Now, using this function, we can compute the magnitude or the length of the vector. So the magnitude of the vector, which is going to be the square root of the sum of squares. So we will return math.sqrt of sum of squares of v. And now let's print the magnitude of y. So let's print the magnitude of y. So the magnitude of y is 9.94 units. So let's get back to our drawing. So the magnitude is the length of the vector, and the formula for the magnitude or the length can be proved using the Pythagorean theorem. So if we imagine that we have a triangle here, then the length of this side of the triangle would be equal to the length of this portion of the axis, and the length of the second side would be this one. So the length of this side will be the square of this side plus the value or the length of this side square, and then you find the square root of that sum, and that is the length of this side. And if you have more dimensions, then you just apply the Pythagorean theorem more times. So the squared distance between this point and this point will be the squared distance between the sum of the squared distances between the origin and this point, and this point and this point, and then the squared distance between this point and this point will be the square distance between this and this, and the square distance between this and this. And if we just sum everything up and then we apply the square root, we will get to the same formula. So the length of this vector will be the sum of the squares of its components on the axis, the x-axis, the y-axis, and the z-axis, and then everything will be uh, and then we will apply square root of that. So it will be the square root of the sum of the squares of these values, if pi makes sense. If not, just try to compute the length of this segment yourself and see that you will get to the same formula, or just look it up on the internet. Just use Google and type formula for the length of the vector geometrical interpretation, and probably there will be other sources which will get into more details. But computer science, we mostly deal with the algebraic form of the vector, not with the geometrical interpretation. So we will not use this geometrical interpretation too much. So so that's why I won't go into too much detail. Now that we have defined the magnitude, uh, we should move on and define the distance between two vectors. So the distance between two vectors, let's say distance between vector v1 and v2, this distance is going to be the square root of the sum of squares of the uh, vector subtraction of v1 and v2. So why is that? Well, the distance between two vectors geometrically can be seen as the distance between the two ending points of the vector. So the distance between vector uh, A and that is not a really good example. This is a better image to illustrate what I want to say. So the distance between vector B and vector A is basically the distance between the ending point of the one of the vectors and the ending point of the other vector. So the tips of the arrows, and you can compute the distance between 2 points in a space using this formula. So you subtract the coordinates on each axis, you square the result of the subtractions, you add everything up, and then you apply the square root. It can also be proved using the Pythagorean theorem, but I won't go into too much detail. If you are just interested, try to Google it up, to Google the distance between two vectors, and just learn more on the Wikipedia, or I don't really, for any source you find. I won't go into much detail because it isn't really relevant for our purpose. Uh, but of course, if you want to learn more, just do it. This is just a brief introduction in linear algebra. Linear algebra is more complex, obviously, than this. There are entire books written just for linear algebra, so it is impossible to comprehend or to say everything in just one video. So if you are interested to learn more linear algebra, just find a book or find a more comprehensive tutorial and follow it, because linear algebra is very useful in data science and machine learning. But for this episode, we are just going to present as much. Now, enough talking, let's test our last function. So let's compute the distance between vector y and vector v. So, so let's print distance between vector of y and v. And the distance between the two vectors is 9. So this was it for this tutorial. In the next tutorial we are going to talk about matrices. So the linear algebra tutorial will be divided into two distinct parts, this one and the next one. I hope you have enjoyed this video, and don't forget to like and subscribe, and see you in the next episode of my data science series. Bye!